Okay. Hi, so my name is Ashwin Devaraj. I am a PhD student at Raman Research Institute. So I'm finishing up my PhD now. And my primary research interest is in looking at neutron stars. I'll tell you about what neutron stars are in a bit briefly. But I use X-ray data or X-ray information in X-rays to understand these neutron stars. Okay. So the main topic here, as far as X-rays are concerned, we are going to look at polarimetry using X-rays. What is polarimetry in general? What is polarimetry using X-rays? Where is it needed, and what causes it, and how does it happen? These are the questions I want to address. So I've divided it into two parts, the talk. One is the physics aspect of it, and then moving on to the astrophysics of it. Okay. So I very often get asked the question, if you want to do astrophysics, what is the basics? Like, how do I get into astrophysics? How do I do astrophysics? And if you ask any astrophysicist, they will give you the same answer: be good at physics first. So developing on physics on a much larger scale is what astrophysics is. So first we need to understand basic physics of what happens. And our basic physics involves the interaction between charges and electromagnetic radiation. So meet Mr. Charge. For our explanation, it is an electron, and electrons, as we know, have a negative charge. Okay? It has a friend who is a proton, heavier and has a positive charge. Okay? So they have another friend, a neutron, okay, which is neutral. It's heavier but neutral. Together, all of these come together and form atoms. Okay? When they're all together, if there's equal number of protons and electrons, you have overall charges 0, right? Charge neutral. So typically what we deal with, or what we see, what we are made of, all these things are all atoms and they're all charge neutral. It becomes interesting when you have charges involved, meaning they are not neutral. Then these things behave very differently. Now, charges are predominantly affected by two things: electric fields and magnetic fields. Okay? And their interplay is what gives rise to all the phenomena we see around us. There is also gravity here, but gravity does not cause radiation. But what I want to say is what happens when charge interacts with electric field and magnetic field, and then in principle what it does as a consequence. Okay? Neutrons, I mentioned, right, are neutral, so they are not affected by the electric and magnetic fields. Electrons and protons are. Here is at the end of this talk, if you are going home, I want you to remember one thing. I want you to remember this statement: accelerated charges radiate electromagnetic waves. Okay? So the radiation that you're seeing, radio waves, you heard of microwaves, you heard of X-rays, all of these are radiation. How are they created? It is created through the acceleration of charges. If you accelerate a charge, it will radiate. This is the sacred principle that you need to just keep in mind. Okay? So how do we accelerate charges? I mean, if you want to accelerate someone, you go and kick them. Right? So they'll suddenly get a jerk and they'll move forward and fall. That's an acceleration. But how do you do it for charges? You can't tie a string and pull it fast, right? You accelerate it through electric and magnetic fields. So this is a small video that shows how, if an electron accelerates. So there are many ways of accelerating it, right? You take an electron, you drag it suddenly, you apply electric field which will drag it suddenly, and then that will accelerate it. You make it move up and down, it will accelerate, right? Because its direction is changing constantly, its speed is also changing, so it is accelerating. So this is a video showing how an accelerated charge will produce radiation. So this charge is moving up and down, okay, and it is producing these red waves that you're seeing as the electric field. What you're seeing parallel to, perpendicular to it, in the green is the magnetic field. So electromagnetic radiation is a combination of electric fields and magnetic fields perpendicular to each other, and then there will always be perpendicular direction in which they are propagating. Okay? So now you can see this here. The frequency at which you oscillate this electron is the frequency of radiation you will produce. Meaning, if I want to produce radio waves, I will oscillate it slowly. Okay? If I want to produce X-rays, I will oscillate it rapidly. Okay? The frequency is basically how many times does it oscillate within 1 second. That is how we talk about electromagnetic radiation. It's a wave. And the frequency is how many times does it oscillate. Okay. One other thing I want you to notice here is there are multiple lines here, right? You can see there are multiple lines here in different directions. So if I basically have one charge here and I move it up and down, it will produce radiation in all directions. And I just pick out one of these things and I go very far away, right? There actually is one specific plane in which it is vibrating. The electric and magnetic fields, electric field is going this way, magnetic field is going this way when you go very far away, right? So just keep this in mind, just consider one of these things and just keep it in mind. We'll come back to it in a minute. So what is electromagnetic radiation? It is basically magnetic and electric fields varying with time. You can see this here. Magnetic fields are varying in one direction, which is here, and electric fields are varying that way. The number of times they oscillate in 1 second is the frequency. And how high the frequency is, how many more times it oscillates in 1 second will tell you the energy of the radiation. So now what happens when you take these electromagnetic radiation and you throw it at charges? So I said charges produce electromagnetic radiation when they accelerate, right? So how did you make the charges accelerate? Apply electric magnetic field. Okay, now radiation is produced, there is one charge sitting there silently. It goes and hits that, what will it do? It will make the charge move up and down. It will accelerate the charge. And then what will happen? Now that will radiate. Okay, so this is how it works. So think about it this way, when you're looking at the night sky, right, there are these stars. So light is produced from there. That light, those photons are reaching your eye and making the particles in your eye move up and down. And those signals are imparted to your brain unhindered, from all the way from how many of light years away. Okay? So the point is, the reason you're able to detect it is that the electrons in your eyes have moved up and down and created that electrical signal so that you can actually identify that's happened. So if it does not interact, it just goes through. For example, you do not see in infrared, it just does not make it work, or lower wavelengths, microwave. You're seeing invisible because it's interacting, making the same changes here. Anyway, moving on. So what happens in a bulb? So I just told you something. Accelerated charges radiate, but in a bulb it's made of atoms. They're all neutral, right? Why is it radiating? So the principle again is that you need accelerated charges. So first thing is that when it is coupled together, you first separate it out by applying a huge amount of voltage across the ends, and then that will heat up the tungsten. And then once that happens, the electrons pop out. And now these electrons, like I said, there is an electric field applied at two ends. So they get accelerated and then they radiate. Okay? So accelerated charges radiate. Now I showed that earlier there are these individual lines that you are seeing in one direction. If there is one single charge accelerating, moving up and down, there are these individual electromagnetic field variations that you are seeing. Now let us say that right next to each other, I throw many charges and make them move up and down. And then I go very far away and I look at the light coming from the collection of these charges. Will I see the charges, will I see only one direction in which electric field is moving up and down, or multiple directions? So all the things are contributing to light. So if one set of electrons are moving in this plane, one set of electrons are moving in this plane, they'll all produce electric and magnetic fields according to how they're moving. So what I ultimately get is a combination of all of those things, electric fields and magnetic fields oscillate in all directions, and then I see unpolarized light. Now let us say I have a device which can cut out everything else except in one plane. Then that is called a polarizer. In optical case you would have seen this, and I'll come to an example in a minute, but what it does is it restricts a very specific polarization to come out. It means that when you have all possible orientations of these electric fields, you are identifying one specific plane, and then that plane in which it is oscillating, that will be the plane of the polarization, and then that light will be called as plane polarized light, linearly polarized light. Okay? So here it is at 90 degree this way, and here it is perpendicular to that. So these are two polarizers. Now can you imagine something? I said that all this contains all kinds of vibrations, all vibration, all directions. What happens if I put this polarizer after this? Can anybody guess what will happen? Sorry? You don't get anything, because there is nothing oscillating in this way for this to capture and let out. So two polarizers perpendicular to each other will cancel out all light, and this we use. I'll get to an example of where we use in a second, but little more about polarized radiation. How do you produce polarized radiation? So like I mentioned earlier, I have a bunch of electrons moving up and down. Oops. One second.
Just use the
Okay.
arrow button.
I think so. I'm so sorry. Yes. Sorry. Right. I'm so sorry about that. So I said you have a bunch of electrons all moving around randomly, and they're all emitting radiation in all directions. So if they're moving randomly, the radiation they emit will be unpolarized, right? Because they're coming from all directions, they're moving in all directions, there's no specific direction that's interested. If you have one single electron moving up and down, the radiation that comes from it will be polarized. But when you have a collection of these atoms and electrons moving around randomly, and you're combining all the light that comes from them, that will be unpolarized light, right? Because there is no specific clear direction. So I would say the emission is isotropic, same in all directions. Next, if I apply an electric field to this, there are electrons. Whatever they were doing, they are vibrating here and there, whatever. I'm giving them a preferred direction in which they want to move. And suddenly, they will do their vibration, but in one specific direction. So the radiation that comes out of that will be polarized. So the breaking of isotropy, same everywhere. When I take that away, suddenly I get polarized light. I give a preference. You need to see that, come back to this diagram, this animation. This line, this plane in which it's oscillating, choose one, and that is the plane of polarization. Okay? So when I am looking at this red plane, that is the plane of polarization. This radiation will be polarized. When I look from very far away, I'll only look at one of these things. Okay? When I go to this box of gas and I apply an electric field, I make all of those things oscillate in the same direction. They're not moving randomly anymore. So the radiation that comes out of them will be polarized. Okay? So where do we really use this? The main idea is that anisotropy, second point. First point, accelerated charges radiate. Second point, anisotropy gives rise to polarization. And I'm not talking only in X-rays. I'm talking for all wavelengths. This is how it works. So what's the point of studying polarization? Polarization is used everywhere. The idea, the concept, and the importance is a lot. Have you heard of Polaroid glasses? Those cooling glasses that you wear. They cut off half the light, right? So if you have unpolarized light, you're cutting off all the light that's oscillating in every plane except in one direction. So 50% of the light is cut off. So when you wear these as sunglasses, you do not get as much intensity. 50% of it is cut down. That's why you have Polaroid glasses. Second thing is that this is a display, what you're seeing here, like a monitor or a watch or any of these things. What happens there is you have liquid crystals. You have small, I mean, each liquid crystals are basically these small objects, very tiny. And then when you apply electric fields to them, they will orient themselves. They will allow a portion of light to exit, and then when you rotate them, they will not allow. Okay? On top of that, when you put a polarizer and you rotate the liquid crystals by applying electric fields, only some specific lights come, and that's how you're getting all of these things. LCD, liquid crystal display, right? So there is one polarizer there on top of the screen, and then you're introducing a Polaroid. So I asked a question a little while back, what happens when I put two Polaroids on top of each other at 90 degrees? You mentioned the light gets killed completely, and that's what's happening here. When it is this way, the polarization axis of the Polaroid as well as the LCD are both in the same line. When it's 90 degree, it becomes black. So polarization, you can see that it's being used for the liquid crystal display. Whereas one other example I can tell you is when you go to movies. The 3D effects that you see is based on two different polarizations that are there. So the depth perception is contributed to it. One eye gets one set of type of polarization, the other eye gets the other type of polarization. And depth perception. If you remember earlier, there used to be different colored glasses, you know, cyan and red, green and red, and things like that. And that would give you a certain weird feeling when you're watching the movies. But here, with using polarization, left circular and right circular polarized light, you get a more clear 3D effect. Okay. So now we move on to the second part. And the idea is about astronomy in general, and then moving on to specifically why X-ray astronomy. So Saurabh had shown a slide about how you have all kinds of, all the wavelengths, how important they are. He showed you a slide where, you know, you go from radio to X-rays, and Milky Way looks very, very different in different wavelengths, right? And X-ray and astronomy or astrophysics is a place where gravity is king. It reigns supreme, and everything that you talk has to be in context with this. And when you go further in smaller regions of that, then you start talking about the other processes that happen. But gravity is the ruler. So why look at X-rays? Why look at the universe in X-rays at all, right? So here is the thing, when you look at an optical, the first telescopes that were made were an optical, right? This is how a specific galaxy looks. When you, by the way, we can look at a very narrow range of this, okay? In the grand scheme of things, we are deaf and blind. That needs to be understood. So when you're looking at the thing in optical, invisible, you're seeing a certain, this is what it looks like. When you start looking at infrared in the electromagnetic spectrum, go to lower energy, lower meaning lower frequency, this is what the galaxies looks like. And when you go to even lower frequencies, this is what it looks like. Now come to the highest energy, X-rays. If you look only in X-rays, this is what it looks like. Can you see that these are two completely different images? If I showed you this on Monday and showed you this on Wednesday and ask you what are these two things, you'll never come up to me and tell that they're the same thing. They're two completely different objects. But the analogy that Saurabh also gave is that a bunch of blind people trying to figure out what the object is in the elephant. You need to put all of these together to see. The cause for emission in X-rays is very different from what emits radio, right? So the idea is to put all of these together and do it in a multi-wavelength. And that's the idea of combining all of these. And our eye can only see a very small range of light over here. Okay. Now, just to get an idea, before we move on to what neutron stars are and what other things are, to get an idea of the scale of things. If the sun is this large, Earth is this tiny. Okay? In the grand scheme of things, the fight you had yesterday morning has no relevance. Okay? The point is that how do you construct this sun? How many Earths do you need to put in? Like this, let's say you take something, the volume of the Earth, and you start filling up an object like this. How many Earths do you need? You need 13 lakh Earths to fill that up. But here is some interesting thing I want to say. The sun is so massive, and you need about 3.3 lakh Earths to fill the sun. Mass, that is how massive. But the sun is not, even though sun is so massive, it is not as dense. You know the density of the sun? It's as much as water. It's full of helium and hydrogen and all of these things. But the density, number of particles, number of grams per centimeter cube is 1 grams per cc, which is just as much as water. It's 1.4, but it's very close to the density of water. I mean, the density of this ground is much higher, but the point is that the sun, the temperature is also much higher. They're all separated out, and the density is as much as water. Now I want you to think of something. I want you to imagine that you are compressing this entire thing to a small area. The mass is the same. The number of all those particles are there. Somehow you're, compressing, pushing it together with in some way to a smaller and smaller size, to the size of the Earth. Okay? If it is almost approximately the size of the Earth, you get something called as a white dwarf. And if you compress it to the size of Bangalore, in fact, Bangalore has become much larger now, about 10 kilometers in radius, right? Then you end up with something called a neutron star. So just keep this in mind. So what are these compact objects? These are end stages of stars that evolve. So stars are bright because of gravity, their gases are being held together, and then they're put together, and then they're being compressed by gravity. Because of that, fusion happens where small atoms of low atomic weight combine together to form larger atoms, right? You have hydrogen combining to form helium, then helium combining to form higher elements. This is what happens. And then when they combine like this, they produce radiation, and that's what we see. That's why the stars are bright, they're shining. So what happens when you can't fuse them anymore? What happens when you don't have enough energy to combine these atoms? They stop and they collapse, right? So radiation they're combining together, gravity is pulling them in, but radiation is keeping them, pushing it out to make sure it doesn't fall. There's an equilibrium. Radiation being produced is stopping them from collapsing. So that equilibrium, when it goes away, when there is no fusion producing radiation to keep the thing stable, it will all collapse. The entire mass of the sun will collapse to a region as small as the size of Earth. And I just told you, you need about 13 lakh Earths to fill the volume of the sun. That entire volume reduces to 1/13 lakh of it, right? That is a white dwarf. If it is heavier, if the fusion has happened, more higher elements are fused, then it will collapse to even smaller radius, the size of Bangalore, right? So the radius of Earth is about 7,000 kilometers. 10 kilometers and 7,000 kilometers. Just can you imagine the difference? So the entire mass of the sun compressed to that small region is what happens when you end up with a neutron star. Now if it collapses further to an even smaller point, you end up with black holes. These objects have slightly different properties, and where black holes are, you watch movies like Interstellar, so radiation, it's so strong, the gravity is so strong, even light bends around it, and if it goes through it, probably does not escape. My specific research interest is around neutron stars and how they interact with the matter around. Because these neutron stars are massive magnets. Okay, their magnetic fields, to give you an idea, the fridge magnet, let's talk about Earth has a magnetic field. The magnetic field of the Earth in some units called Gauss is about 3 or 6 Gauss, within 3 and 6 Gauss. The fridge magnets that you have will probably have about 1000 Gauss. MRI machine will have about 100,000 Gauss. Okay, so I'm just scaling it up slightly. You know the magnetic fields of neutron stars typically? 1 followed by 13 zeros. That's how many Gauss? 10 power 13 Gauss or 10 power 14 Gauss. There are massive magnet monsters in the universe. And you understand, these things interact with the matter around them in crazy ways. Okay. Having said these things, I want you to get to one other point. of why do we even have to look at compact objects in X-rays? Like, why not look at it in optical? The reason is the following. Firstly, all the fusion has stopped. All the light that you're seeing, like the sun, it stopped fusing. So fusion is there is no direct way of looking at it. You won't see it in optical light. It stopped producing that radiation. There's no radiation that escapes from the surface anymore. And black holes don't emit any radiation. They're completely absorbing everything that's coming around it. So how do you see them? So to understand the principle of that, why we choose X-rays to look at it is the following. Now, have you seen this? You take a ball and you drop it from a height. Okay? You probably pick it up and you don't see much. But you hit it hard, and you hit it hard multiple times. What happens? What do you feel? Anybody? The ball becomes hotter, right? You feel the heat in it. You can't see the heat in it, but when you look at it through infrared glasses, you start seeing it becoming hotter. Now, let me make an exercise. I am saying that you're dropping it on Earth with whatever mass there is. Now, Jupiter, which is 300 times more massive than the Earth, you need 300 Earths to make Jupiter. I compress that entire mass to the size of the Earth, and I drop it from the same height. Now, mass is higher, the ball falls on the ground, it will become hotter, right? Because the gravitational pull is much higher. So that potential energy is getting converted to kinetic energy. When it hits the ground, it's giving away that kinetic energy, and then it heats up. It's literally like you taking a ball and hitting it with a hammer. That same amount of energy can be produced by dropping it, right? So when you go and hit a hammer on a rubber ball, it heats up. Now what happens when I do it for Jupiter? So for Earth, it's probably emitting in infrared. Jupiter, it's 3 times higher, so higher frequency of radiation. Now what happens if I compress the entire sun to the size of the Earth or smaller and then drop that ball? That ball will reach half the speed of light. Okay? So if it reaches half the speed of light, can you imagine the velocity, how fast it's coming? It takes 8 minutes for the radiation from sun to reach the Earth. It will take twice the amount of time for the ball to reach the same distance. It will reach such high velocities, very, very high energy, and that will start producing X-rays. By the way, when the ball falls, it will be completely ripped apart. All the atoms will come apart and electrons will come apart, and they'll all hit the ground all at once. And then that energy that it produces will be X-rays. Just like how the ball is producing infrared over here when it's hitting the ground, those will produce X-rays. And that's how strong the gravity there is in neutron stars and black holes when it absorbs the material. This is why we are looking at these objects in X-rays. So if you have an isolated neutron star sitting somewhere, can you really see them? No, you can't. It's not easy. It depends on what process is happening, but this accretion process is when you have one object, neutron star, and one main sequence star, which will supply material to it. You have a sun-like star, which will give a material, and then you have the compact object, which will burn it. Then you'll start seeing it. Okay? So this is an example where you have a compact object, like something like the sun, and then you have a neutron. If there was a neutron star nearby or something, it will pull all that material, it will form a disk around it, and then it will burn all that material, producing X-rays. And that's why we are looking at it in X-rays. And I told you something earlier, that isotropy will result in unpolarized radiation, anisotropy will give you polarized radiation. So where is the anisotropy? I said neutron stars are massive magnets, which means the way matter will go onto the neutron star, fall onto it, there is a preferred direction. The way it gets burnt, there is a preferred direction. The way it's emitted, there is a preferred direction. This anisotropy, this break in isotropy is what causes polarization. See, when you're looking at this, the light that's coming from here, right, you can't really tell the polarization of it. But I bring a Polaroid, then I'm able to recognize it. So by bringing a Polaroid, I can really tell what the technology is being used here. So it gives you more information about what there is, apart from just the visible. I'm separating out that all those photons of light into 2 parts. And then I'm trying to understand what causes these individual parts. So I get a better insight about this. This is what is called an active galactic nuclei. There is a supermassive black hole in the middle of the galaxy. When that burns all the material and emits that will also produce polarized light, because again, these are not spherically symmetric, right? There's a certain direction you can say, jets are in this direction, disk is in that direction. When light from this gets emitted onto the disk and then gets scattered out, there's actually a directionality I'm giving you. It's not uniform in all directions, like the sun, for example. It's coming spherically symmetric, right? So that's why we expect polarized radiation, and we want to look at X-ray polarimetry. One important point here, unlike visible light, where you have lenses, light passes through it, you bend it, you focus it, and you do all kinds of things. You have polarizers, which is going to separate out these polarizations. In X-rays, the X-rays do one of two things. They will either pass through or they will get absorbed. Okay? You cannot manipulate X-rays as easily as you are doing optical light. So the technology that you need, the common sense question will be, why don't you have X-ray polarizer? Just put it and send it on space, no? But then that doesn't work, because X-rays either get absorbed or they pass through. So you need more complicated, sophisticated technology to deal with it. So this instrument, Polix, was built to look at these compact objects in X-rays, so that we can understand what's really happening in some of the processes there. So Gopal Krishna will continue from here. He's an engineer who is involved in Polix right from the beginning, and he will tell you of the details about the instrument and working and things.